All right, thank you all. To our next to last Courtier this semester. We're very pleased today to have Dr. Sarah George as our speaker. And Dr. George received her bachelor's degree from Wellesley College and then joined the Horton mob at UT Austin for her PhD, where she worked in Northern South America. And we'll be hearing about some of that work today. Sarah came here to U of A as a postdoc in the Lasertron lab starting in August of 2019, so 2.5 years ago. And she's just really torn it up as a postdoc. She's done an amazing job. She's worked with dozens, hundreds of researchers coming through the lab on all the different projects with her students. They've done a great job with that. She started up her own projects in various parts of the world. See if I can name them all. I think she's working in Turkey, the Himalayas, the Grand Canyon, the Canadian Cordillera, Patagonia, so all of these kind of independent projects that she started up. She's also helped us teach Lasertron short courses at GSA for the last 2 years, both in person and remote. Those went very well. We've had a lot of fun doing some outreach activities that Sarah took the lead on at Mansfield. We had a couple of fun evenings with middle school students talking about Earth time and rocks and minerals. Sarah did a great job of reaching out to these students to set that up. She's also had a chance to do some teaching. She co-taught Geo 251 with me a 1.5 years ago, I think it was, and we had a great time co-teaching that, even though it was a COVID world where we were the only ones in the classroom, but it was still fun. And then Sarah has taught Indiana University's field camp 2 different summers and helped them, I think, put together their first offering of a virtual field camp. That must have been interesting. And Sarah's had lots of great news recently. She's a PI on a NSF proposal that was just funded from the tectonics program at NSF. She'll be working on that starting this summer. I won't tell you the details, but she's received 3 different offers for faculty positions just here recently, and I'm not going to spill the beans on where she's going or what's happening, but maybe she'll tell you eventually. So with that introduction, Sarah George talking about upper crustal responses in South America.
Thank you guys for having me, and thank you for the kind introduction. So I'm going to be focused today on South America and these zones of flat slab subduction along strike. So of course, South America is characterized by a large subduction zone that spans over 8,000 kilometers, where oceanic lithosphere is being subducted under continental crust. And what I want to point out in this first image here is just these large ridges on the seafloor. So the seafloor is not flat here. It's quite, there's quite a bit of topographic relief. We practiced this. It worked before. Okay, so this has been kind of a pandemic project for me, trying to figure out what we could do when we couldn't go to the fields. It's been a lot of fun. I've gotten to work with 3 folks that I've never worked with before, including Will Struble in the department, and learn a lot of skill sets that I've never thought about before, including some geomorphic indices. So I want to start off with this map of the ocean floor, and it just shows these areas of over-thickened oceanic crust in black polygons. So these things take up on the order of 10% of the ocean floor. They take shape as large oceanic plateaus, extinct spreading ridges, hotspot tracts, and these things range on the order from 10, 15, even 30 kilometers thick. So these are extremely thick oceanic crust. And as you probably have taught recently or know from your Geo 101 class, most of the oceanic floor is geologically quite young. Only about 65 million years is the average age of the seafloor. And this, of course, works because we have places where we can generate new oceanic crust along mid-ocean ridges, and we have places where we can destroy oceanic crust along subduction zones. So this requires, of course, that this thick oceanic crust is currently and has been interacting with these subduction zones. And indeed, if we go to the modern Circum-Pacific today, where most of our subduction zones are located, roughly 10% of these are occupied by these thick ridges that are subducting under continental crust. This presents a bit of a problem. Of course, if it's thick, it is buoyant and it doesn't want to subduct. If you look at any of these, early calculations from going back to the 70s, basically they say if it's young or thick or too buoyant, it's not going to want to go down the subduction trench. So when it does come to the margin, it has two options. One option is that it can actually accrete to the margin and it can start behaving as part of the margin, right? So that's what happened up in the northern Andes. This big green swath here is actually underlain by oceanic crust that was accreted about 75 million years ago and has since this takes up most of the northern Andes today, really quite amazingly. That's all oceanic crust. What I'm going to be talking about today is the other option, of course, when these ridges subduct. This is happening currently today all along the South American margin. I'm going to be focused on the Nazca Ridge, which is currently subducting under southern Peru. I'm going to call this process ridge subduction. Different folks have different names for it, which seems weird, but basically thick oceanic crust going down, ridge subduction. Okay. This can drive a secondary process, and I'm going to try and differentiate between these two processes. This becomes a bit complicated because, as we'll see, they overlap both temporally and spatially. And this is because the process of ridge subduction often drives this other process, which we're going to call flat slab subduction. So flat slab subduction is simply when the subducting slab shallows its dip and comes in at a subhorizontal geometry underneath the continental crust. There's a whole bunch of other causes of flat slab subduction. We're not going to worry about those today. We're worried about these cases where ridge and flat slab are kind of linked genetically. So flat slab subduction has some really interesting consequences, and these are quite well documented. One of the major ones happens to do with the magmatic arc, both its location and the geochemistry. So if you start off above a typical subduction zone, dipping around 30 degrees, you're going to start with this kind of narrow calc-alkaline arc. As you begin to flatten your slab, you actually broaden the zone over which melting can occur. And the compositions typically change into these more atachitic compositions. Through time, you will actually entirely pinch out that asthenospheric mantle between the overriding and subducting plates and shut off magnetism and volcanism entirely. We've actually seen this happen. Well, we haven't seen this happen. We have records of this happening in many places. One of the best documented ones is, of course, the Laramide province of the Western US. And in the Laramide, we basically have the magmatic arc starting off near the trench. It migrates over 1,000 kilometers inboard. It ultimately shuts off for a couple of million years. And then as the slab returns to a normal steep dip, the slab rolls back and the arc is reestablished at an outboard location. Tucson is here for reference. Another major change that's typically associated with these flat slabs is the change in structural style. So in a typical Courtier origin, we often have shortening accommodated on large ramp flat faults, right? Basically deforming sedimentary cover. One of the major changes that seems to be associated with these flat slabs is a change towards basement involved large scale reverse faulting or thick skin deformation. One of the places where we can see that actively going on is down in the Sierras Pampeanas of Argentina. So this area is a modern flat slab, and this is out in the Foreland Basin, and you see these big, beautiful basement-involved reverse faults that are partitioning the Foreland Basin, basically structurally bringing up those units. To the south, where that flat slab hasn't been active, the basin's not partitioned, right? Okay, so we have some ideas of what's happening in the arc and what's happening in the foreland and structurally with these flat slabs. I would make the argument that we know comparatively less about what's going on in the forearc and the hinterland region. And so that's what I'm going to spend most of my talk on today, focused on kind of this region here and what might be happening there. So these flat slabs turn out to be really important for a whole bunch of different things. I've kind of covered the pure geological basis that in the past few slides. They're also really important for seismic hazards in the state of stress of the crust. So Sue Beck's group and others have shown that these are really fundamental in changing how shortening is accommodated. And then from an economic standpoint, these things are have a pretty big impact on the mineralization. So in these blue stars here, I'm showing the large copper and gold deposits in South America. Note that both of these bands are directly above modern flat slabs. Okay, so overarching question here, this is big scale. What are the geologic responses to flat slab and ridge subduction? And to answer this question, we're going to turn to the Peruvian flat slab. The Peruvian flat slab is the largest active flat slab on Earth, and it spans over 1,300 kilometers along the South American margin. Now, the Andes are only 8,000 kilometers long, so this is big, right? It's associated with a major gap in the volcanism. So these red triangles here are the active or quaternary magmatic arc. And you'll notice that in Peru, there's no triangles, there's no active volcanism. Another feature that we see is, of course, that the geometry is flat. That's why we call it a flat slab. So that's reflected in the Benioff contours here. So you can see that they're deflected way out to the right here, basically reflecting that flat geometry. I'm going to keep those on kind of throughout the talk as a spatial guide for you guys. At the southern terminus of the flat slab, we see one of these buoyant ridges that's subducting currently called the Nazca Ridge. This thing is big. It's about it rises about 1.5 kilometers off the ocean floor. It's about 18 kilometers thick. It's been subducting for quite a while. And so we think that there's a large reason to think that there's a relationship between the geometry of this flat slab and the presence of this Nazca Ridge. Okay, so briefly, I want to walk you through just some basic topographic observations and some observations about the downgoing slab. I'm obviously not a seismologist, but this is my attempt at doing seismology, so bear with me here. I'll show some fancy pictures from Susan Beck in a minute here. So we start off at this band 1. This is within the active zone of flat slab. You can see this because the Benioff contours, of course, are deflected out to the east. What we see is that the slab is in fact flat, but it sols out at about 100 kilometers depth. So it's flat, but it's flat at a pretty deep depth. Same in profile 2 here, sols out, but at about 100 kilometers. Then we get directly above the Nazca Ridge, and we see this flat geometry, except it's at like 60 kilometers depth. Okay. We go down to profile 4 here, and we return to normal dip, about 30 degrees. Another thing to point out here are in these swath DEM profiles is directly above the Nazca Ridge, we have an uplifted forearm. This also shows up in map view. Notice that the forearc is subaerially exposed there, but it is not in the rest of the flat slab region. And we also have an uplifted foreland, which you can see that's the Fitzgerald Arch, this big domal uplift that we have in the Foreland Basin, which is almost certainly related to subduction of the Nazca Ridge. Okay, so if we look at the fancy tomography, not my version of tomography, we see that all of these trends hold true, right? So the slab is not flat here, but rather it's got quite a bit of relief on it. So this was first observed by Andres Guster back in 1999. And here's 2 degrees south here, going south all the way down to 15 degrees south. And what he noted is that if you just plot earthquake depth, you see that there is a sag in the slab kind of in central Peru. This has been confirmed using more modern imaging techniques. Some of the work that Sue's done has also shown that there's major tears within the slab. So this slab is not a homogeneous plane, but rather has tears and sags along it. Above the ridge, however, we have quite a different story. We have a nice continuous slab as seen in receiver functions. Note that it's really coming in at about 60 kilometers depth. Basically, this requires that we actually have some crustal thinning here, as well as displacement of lithospheric mantle, which is really quite amazing. So things are quite coupled above this subducting ridge. So as I said before, the slab is not uniformly flat. There is topography on it. Here's kind of what this might look like. So this is north and this is south. We have the Nazca Ridge coming in. This is one of these coupled regions, or that's what I'm going to propose. We have this major sag that's in the central part of Peru. In the north, we have this other posited It's not a ridge, it's a plateau. I'm going to call it a ridge for this talk, called the Inca Plateau. This thing is a fully subducted seismic asperity that would be fully subducted and sitting currently under northern Peru. Okay, so the questions I want to ask are first of all, what was the forearc and hinterland response? I've left this question intentionally generic, not talking about like what did it, just what was the response to this process, be it ridge subduction or flat slab. And I'm going to look at this basically using two types of data sets, thermochronology and geomorphology. And I'm going to try and see whether drainage networks responded, because drainage networks are super sensitive to perturbations and rock uplift. And then secondly, I'm going to look at thermochronology to try and figure out whether there is elevated hinterland exhumation. And then if so, this is the whodunit question. Was it the ridge or was it the flat slab, right? Okay, so to get at these questions, we're going to start off with geochronology, specifically geochronology on arc rocks. As we talked about before, when a flat slab is established, it essentially extinguishes the magmatic arc, right? And so the timing of arc shutoff is essentially a proxy for when that slab became flat. The second thing we're going to look at are published plate motions. These are going to give us the location of the ridge through time. These are pretty well established by this point. The next thing we're going to look at is geomorphology. Again, landscapes respond to perturbations. And then finally, thermochronology. This is going to give us the timing component of all of this, right? When did it happen? Okay, so this is my cat, Pacha. I want you to keep her in mind as we go through this talk. She is currently sitting underneath a carpet, right? And she is creating this elastic or transient strain within the carpet. As soon as she gets hungry and decides to leave, that carpet's going to relax back down behind her, right? It's going to subside in her wake. That's very different than her destroying my couch, where she is inducing plastic or permanent strain. This would be essentially these upper crustal faults that are moving and creating these discernible permanent strain within the rock record. And I'm going to make the argument, here's basically my conclusion slide, that is that Nazca Ridge migrates, which we'll see that it does. It basically creates this uplift and elastic strain within the upper plate. It's basically buoyantly pushing the upper plate up. It's going to create rock uplift and exhumation. And then as soon as it propagates past, things are actually going to fall off the backside and subside in its wake, okay? So this ridge subduction, I'm going to argue, is the primary driver of exhumation, drainage reorganization, and this kind of transient uplift with evidence for collapse in the wake. So to get us oriented on some geomorphic features, I'll come back to these at the end of the talk, but I just want to orient you with them right now. We have the region of flat slab roughly in this area, the Nazca Ridge subducting in the south. We have two major basement-involved reverse structures in Peru, the Almendro-Humbilla faults, where basically the entire eastern Cordillera is brought up on a single, well, not a single fault, but a single fault system. And then the Shira Mountains, which are basement-involved reactivated Paleozoic structure that are reactivated in the Miocene and currently are partitioning the Foreland Basin. We have the Fitzgerald Arch, which I referred to before. It's kind of this domal uplift of the Foreland Basin. You can see it based on these big alluvial fans that are feeding off of it. We have the Abankai Deflection. This is a big rotational axis in southern Peru. If any of you have been to Machu Picchu and been amazed by the relief there, this rotational axis is why there's so much relief. It's driving active rock uplift and incision of river systems. And then finally, we have the Courtier blanca normal faults. This normal fault has some of the highest, well, has the highest topography in Peru. And if you're wondering why there's a large normal fault over a big flat slab, that's a great question and is one of the reasons why I think that there's major extensional collapse on the backside of these ridges. Okay, so we're going to start off with geochronology. The way that I'm going to show this is igneous age is plotted on the x-axis going from 0 to 30 million years ago. Distance from ridge axis is going to be plotted on the y-axis. And here you see the Nazca Ridge kind of shaded in this gray color here. There's a whole lot to tease out of this. I'm not going to get into the weeds. I'm just going to make the simple observation that the arc clearly shuts off first in the north and propagates southward through time, basically following the path of the subducting ridge, which we'll see in a few slides here. Notice that the Courtier of Blanca, shown in this red box, has younger exhumation or younger ages in it. Those aren't actually real igneous ages. Those are cooling ages, but people haven't classified them as such, so they have to live in this plot, unfortunately. Okay, so next we're going to look at basically the location of the subducting ridges through time. The convergence vector here is oblique to the trench, and the result of this is that the part that's orthogonal to the margin is going to be accommodated in subduction, and then the other portion is actually going to force this ridge to migrate along the trench. So that's what you're going to see in the next few slides here. So we start out at 15 MA. The Nazca Ridge has just reached the trench up in kind of central Peru. By 11 MA, it's marched southward, and the Incan Plateau has showed up at the trench in northern Peru. So these are things that are inboard of land or subducting, right? I'm just not good enough graphically to show this. The Inca Plateau essentially is migrating directly inboard, while the Nazca Ridge is going to continue to sweep southward. And we get to the current location, which looks something like this, okay? So this is essentially the setup for our hypotheses, which is simply that this buoyant crust arrives around 15 million years ago. It starts migrating southward. And so any of the signals that are associated with the ridge should also migrate southward through time, right? It should essentially be a pulse in the rock record that is there, it's transient, and then it's gone. That's very different than what if the flat slab were causing these processes, right? If the flat slab's causing it, then it should start earlier in the north, propagate southward, but then should continue to be active over all 1,300 kilometers of the flat slab. Okay, so let's dive into the geomorphic indices. We're going to go with two of the most basic geomorphic indices here. We're going to use the catchment average channel steepness, which is exactly what it sounds like. And generally, these things correlate with erosion rate. So higher catchment average channel steepness, steeper channels, higher erosion rates. The other thing we're going to look at are the channel hypsometries. This is basically just the river profiles along strike. And essentially these hypsometric profiles reflect drainage stability. So the way that this works is for channel hypsometry, we plot the normalized area on the x-axis versus the normalized height or elevation of the channel on the y-axis. And generally, older, more stable channels show this concave up morphology, whereas more tectonically active, youthful landscapes have channels that show concave down morphologies, essentially reflecting that uplift or a pulse of exhumation. Okay, so here I'm showing the KSN or catchment average channel steepnesses. Again, I'm showing these Benioff contours to define our flat slab. The Nazca Ridge is coming in here. And this is where the Incan Plateau shows up. This is where the Nazca Ridge shows up. And I'll leave those all on for points of references throughout. So there's a whole lot to tease out here. It's hard to look at something so big and not get flustered by all the colors. There's a few key observations I want to make. South of the flat slab, we have predominantly blue, purple, and dark green colors reflecting relatively low catchment average channel steepnesses. Up in the northern part, we also see those blue and purple colors. Towards the ridge, increasingly towards the ridge, we get into these bright greens and yellows reflecting steep channels, right? More active erosion. So I think that there is a rough trend here where we have an increase in channel steepness, basically towards the present location of the Nazca Ridge. And then this area to the south, again, is relatively low catchment average channel steepnesses. Okay, so now I'm plotting the hypsometric profiles, and I've kind of binned these by latitude. My crude latitude bins are labeled over here on the left-hand side. As before, there's a whole lot of things to pull out here. I'm going to help annotate on some arrows for us. So these concave up channel morphologies, these red arrows, basically older, more stable landscape. Note as you're above the flat slab, all of a sudden you get all of these concave down morphologies. You also get it directly above the ridge, basically reflecting this more juvenile landscape that's come through. Okay, so next we're going to turn to Beryllium-10 cosmogenic nuclides. I've never done this myself. This is just a compiled data set. But basically, in a well-mixed stream catchment, the Beryllium-10 composition of detrital quartz reflects the average erosion rates of a watershed. This is typically true on the timescales of from about 1,000 years to about 100,000 years. So relatively small on the timescales that we're thinking about. So there's been 67 catchments published in the west draining catchments with Beryllium-10 cosmogenic nuclides. So this is what this looks like. On the left-hand side, I'm showing the same kind of map view. On the right-hand side, I'm showing a cross plot, basically cross-plotted versus latitude. I don't know, maybe there's a crude southward increase here, but maybe there's not, right? It's kind of hard to tease out a signal. That's fine. These are short time scales, perhaps not on the time scale that we would expect to see for these ridges, which are propagating at millions of years instead of hundreds of thousands of years. So just to recap what I've said so far, we've got this really large flat slab, right? It's active over 1,000 kilometers of strike, or more than 1,000 kilometers of strike. We see these youthful, smaller, steeper drainages with higher erosion rates above the flat slab, and they seem to increase towards the actively subducting ridge, right? So all of these indices seem like they're increasing towards this actively subducting ridge. Currently, we have no timing constraints on any of this, right? I've just shown you that there's trends here. So that's what we're going to dive into next. And the way that we're going to do that is using regional thermochronology. So thermochronology essentially dates the passage of minerals to the upper crust. The way that we've got two different systems that we're going to be looking at: apatite uranium, thorium, helium, and apatite fission track. These two chronometers give passage to the upper kind of 2 to 5 kilometers of the crust, or basically have closure temperatures corresponding from about 120 degrees C to about 40 degrees C. The way I want you guys to think about these are that younger cooling ages are going to be a proxy for more recent exhumation. So the younger the ages we see, the more recently the exhumation happened in an area. Okay, so I'm showing the same kind of plot as before. This is the apatite fission track system. This is the higher temperature of the two chronometers, basically dating passage from about 5 to 4 kilometers through the upper crust. I'm showing cooling age from 0 to 100 on the x-axis, distance from ridge axis again on the y-axis. The key point I want to make here is that south of the ridge and above the ridge, we have tons of Mesozoic ages, right? Everyone see that? North of the ridge, those Mesozoic ages are almost entirely absent. This basically suggests that there's been more exhumation in this part than this part, okay? We're going to see the same trend again in the apatite uranium, thorium, helium data set. Now, apatite uranium, thorium, helium is dating closer to the surface, 2 to 3 kilometers within the crust. So this is basically the last gas that getting to the surface. What we see here is really quite striking. So going from 0 to 100 MA again. South of the ridge, we've got ages ranging from 80 MA all the way down to near modern. North of the ridge, within the flat slab, almost all of the cooling ages are less than about 15 million years old. So this means that this part of the mountain belt has seen a lot more exhumation a lot more recently. And that actually requires 2 to 3 kilometers of exhumation in that part in the last 15 million years. Okay. I'm going to take that same data set now, the apatite, uranium, thorium, helium data set, and I'm going to plot it in a slightly different way. I've basically taken this and binned it by latitude. So the ridge axis is here. These are basically shown as histograms. So this is 0 to 200 kilometers north of the ridge, 0 to 200 kilometers south of the ridge. And I've gone ahead and drawn in these peak ages on the youngest, basically the youngest peak within the data set. Again, there's no old cooling ages older than about 15 MA north of the ridge, requiring this 2 to 3 kilometers of exhumation up there. Okay, now what I'm doing is I'm annotating in the arrival of these ridges. So this is the Nazca Ridge. It arrives 200 to 400 kilometers north of the ridge around, I don't remember, about 15 million years ago, 14 million years ago, and it propagates southward through time. This is the Inca Plateau showing up. The key point I want to make here is that generally these age peaks actually young southward with that ridge. They generally follow the trend of that ridge. The other key point here is that they don't continue to exhume to modern, right? They do down here, down where the ridge is subducting, but they don't in the north. So basically it's this pulse of exhumation. It comes through following this ridge and then it shuts off as the ridge is propagating past. So I think that this, along with the geomorphic indices, suggests that this ridge is really one of the primary drivers of exhumation in this region. Okay, so just to recap what we saw, again, big flat slab, smaller, more youthful channels that increase in slope towards the current position of the Nazca Ridge. And then these thermochronometric ages seem to give us timing that basically requires that the Nazca Ridge is the one that's driving this exhumation. Okay, I don't want to get too in the weeds here. For those of you in the flat slab community, I'm sure you are familiar with these terms: end loading, basal shear. The key point here is that these would cause plastic deformation in the upper crust. They would require upper crustal shortening. There's another type, right? Maybe just this buoyancy effect. Maybe this ridge is so buoyant that it's actually just pushing up on the upper crust, creating some rock uplift and erosion up there. And so I want to talk briefly about how exhumation is accommodated. Is it accommodated on surface breaking faults, or is it accommodated perhaps in this more buoyancy driven process or some sort of lower crustal process? Gets really complicated quickly. Yeah, just to remind you of the two end numbers. Okay, so what we're going to look at for this are age elevation plots. Basically, this is a way to look at thermochronometric data and to think about how this data reflects different mechanisms of cooling. So we have age on the x-axis and elevation on the y-axis here. Without getting too much in the weeds, surface breaking faults basically require that when you go to higher elevations, you get older ages. That's the expectation, because those rocks cooled first, right? They got to higher elevations sooner. What we see in the eastern Courtier and the foreland, so the stuff to the east, is indeed that's true. You go to higher elevations and you get older ages, okay? That's great. These things were cooled on surface breaking fault structures. When we go to the western Courtier and the forearc, the stuff to the west, the opposite trend is true, okay? It's crude, I'll admit it. If we look at individual drainages, this trend does hold up. So basically you go to a higher elevation and you get younger ages. The easiest way to do this is that it's a landscape response, maybe headward erosion. That could be driven by perhaps buoyancy of the slab pushing up. That could be driven by some sort of midpoint migration. The key point is that there's no surface breaking ruptures. And it seems like regionally this is true, where a lot of the exhumation that we have towards the west is not accommodated on individual fault segments. So let me give you an example of that. This is some work from Arne Scherenberg, who did some work up in the Marañón fold thrust belt, which is a fold thrust belt located in the Western Cordillera in central Peru. And this map is really hard to read on a screen like this. These pink volcanics that are coating everything are called the Calipri Volcanics. They range in age from Eocene to Miocene. but they blanket everything. And they basically show that this fold thrust belt, in terms of being structurally active, in terms of individual faults moving, was dead by the end of the Eocene. And yet, almost all of the cooling ages that come out of this area are Miocene. So something has happened here that is uplifting this landscape, causing rock uplift, despite the fact that this fold thrust belt is essentially dead. Okay, so what I want to do now is I want to work back through the same kind of slide sequence that I started with, showing the migration of the ridge. And I want to annotate in some of those geomorphic features that we talked about earlier in the talk. So the Nazca Ridge shows up 15 million years ago, and almost immediately right inboard of that, there is early exhumation documented in the Courtier of Blanca. This is the area that later becomes the big normal fault. At this time, it is not. In fact, there's no structures that are known from this time period in this area. The Inca Plateau shows up at 11 MA, and almost immediately we have exhumation on the Almendro-Humbilla fault. That's the basement-involved reverse fault that brings up the Eastern Cordillera in northern Peru. The reason we know this is some work done by a postdoc in this department, Federico Moreno. He's worked on some of the intermontane basins there. Besides a change in sedimentology across this interval and a change in paleocurrent directions, we also see a major change in provenance, where sediments were being derived entirely from the west, and then all of a sudden a huge introduction comes in from the east, right? So that's that Eastern Cordillera coming up, partitioning the Foreland Basin. Okay, so we continue through time. Our Nazca Ridge has now propagated southward again. We get uplift in the Shira Mountains, that other basement-involved Foreland Basin structure. Interestingly, right after it's propagated through this area, we actually get extension in its wake. This is exactly when that Cordillera Blanca normal fault, this big normal fault above a zone of flat slab subduction, kicks off. So this kicks off at about 6 million years. We continue propagating southward. We get uplift in the Fitzgerald Arch, which is that domal uplift in the Foreland Basin. And we also start to get major exhumation in the Abankai Deflection, which is that major rotational axis where Machu Picchu is located. So what I find really interesting is that even when we look at the modern expression of this landscape, we see all of these features that seem to indicate essentially collapse in the wake of this ridge. So in addition to the presence of the Cordillera Blanca normal fault, which I think is really interesting in and of itself, and in addition to the tomography, which clearly shows that the slab is not this uniform thing, but has these big slabs and tears within it. We also have mantle-derived helium in hot springs of the Cordillera Blanca, so that would be located up here. There's multiple ways to get mantle-derived helium, right? You can get it from continental lithospheric mantle, or you can get it from a stenospheric mantle. But one of the options is that it is simply a stenospheric mantle contributing. The other thing is the morphology of the coastline. It shows up quite well in this figure. So this is all a big forearc, right? It's a big homogeneous forearc. The only difference is that north of the ridge, it's all subaqueous, it's underwater, it's marine, right? Right above the Nazca Ridge is the only place that this forearc is uplifted, subaerially exposed. Okay, so I only have a couple more slides here. I just want to briefly talk through kind of mechanistically how I'm viewing the system. And I want to start off with the forearc again and just show you some examples of how we know that this forearc does have relief on it and it's directed right above the current location of the Nazca Ridge. So there's been a whole bunch of studies done. There's well-preserved terrace deposits all throughout the length of Peru. Geomorphologists have been working here for ages, dating these terrace deposits. These terrace deposits that are shown up here are on right above the current position of the Nazca Ridge. But when you go along strike and you look at, for example, the MIS 5E terrace deposits, these are, I'm not good with my marine isotope stages, but I think this is about 100,000 years ago. So these are dated to terrace deposits that are about 100,000 years old. We have north right here, we have south down here, we have the current location of the Nazca Ridge right here. These black dots are the MIS 5E terraces. They're all basically at the same elevation. You hit the Nazca Ridge and all of a sudden they're elevated to 80 meters elevation, which is much higher than anywhere else, right? Okay, I'm really fascinated by this rotational axis, this Abankai deflection. This Abankai deflection, which I've schematically shown here as this sinistral rotational axis, it happens to correspond almost exactly with the location of the transition between a shallow and a steep slab. Why would this matter? Well, if this region is coupled and this region is slipping much more easily, if this region is essentially tied to the upper plate, not slipping as easily, not subducting as easily, you would expect to get essentially a left lateral shear zone there, which might cause rotation in the upper plate. We do get these on the seafloor. This is some work by Erman and Furlong up in Alaska, along the Aleutian Trench. We're looking at the subducting slab here, but they have one of these cases where they've got this big locked zone, this big asperity on the seafloor, and they've got this other zone that is freely subducting underneath the trench. And then they get these large strike slip earthquakes along this margin. And they've postulated that there probably should be upper plate rotation associated with this, but they haven't been able to document it. But I think Abankai deflection is one of these cases that might be the upper crustal expression of these essentially shear zones going from coupled to uncoupled at depth. Okay, I think I've got a conclusion slide after this, but I do want to just briefly stop here and talk through this. So this is essentially a schematic view of the margin, right? We know that the migration of the Nazca Ridge has been migrating southward through time. And in my view, these ridges are causing essentially physical uplift, rock uplift in the overriding plate, or excess erosion there, if you will. And then as soon as those ridges propagate past an area and the topography essentially falls off the backside, it actually goes into a state of collapse. The seismologists and the geophysicists have been telling us for a long time that this slab is not homogeneous and that we almost shouldn't expect the upper crustal responses to be homogeneous. So I think that these ridges are doing a lot more damage in these flat slabs than they're given credit for. I think that they're driving kind of these other processes that haven't gotten the attention that they deserve. Okay, just to put this in some text, I think enhanced exhumation and drainage reorganization occurs above these subducting ridges, and that might be concentrated within a large flat slab, right? So you have 1,300 kilometer flat slab, but you only have exhumation right concentrated above these little areas. I think that after these ridges propagate past, you have little persistent coupling between the downgoing and the overriding plate. Essentially, the slab starts failing. And I think that this is evidenced by these submerged forearcs, the sagging slab, the Courtier blanca normal fault, and this change to reduced exhumation after these ridges pass. And then finally, I think that these steep to shallow transitions in the downgoing plate might actually induce upper crustal strain, might actually create these large rotational axes. I didn't talk about it. There's another one of these rotational axes in northern Peru that's even less understood. I didn't mention it because we don't know the timing on it. But I think that this is a really interesting question about how the downgoing asperities interact with the overriding plate. And with that, I will take any questions. Plenty of time if you guys have them.
Sure, let's start with student questions. So any students have questions? Now is the time. Yeah.
Is there any sort of correlation in those hypsometric curves between how concave they are versus channel length? Like, because presumably the shorter ones will respond faster, and so they'll get back to concave. I'm just trying to explain why there's such a massive spread in the.
Yeah, no, that's a great question. Yeah,
Sarah, if you can repeat the question.
Oh, sorry. So Rob asked the question of, is there any correlation between channel length and the differences in concavity on the channel profiles for the hypsometric curves? Great question. There probably is. I think that we've dealt with it so the catchment average channel steepnesses, we've dealt with that issue. So those are catchment average.
Sure.
For the channel length ones, almost certainly there's some degree that's influence there. They are normalized over both their length and their area. So, right. So it's normalized area versus normalized length. So I'm actually not sure, but it's a good question to ask.
Student questions?
Is the Carnegie Ridge to the north like too far away to have an impact on like some of those trends, or like it should be just to the southern branch?
Yeah, totally. So the question was, the Carnegie Ridge, does it have any effects on these trends that you're seeing? So the Carnegie Ridge, for those that can see it, is this ridge coming in right here. That's essentially the Galapagos hotspot tract, which is currently subducting under Ecuador. It is too far, it's out of all of the map views that I've presented essentially. It does definitely affect the estimation on that part of the margin. This has now been documented by Richard Spikings and more recently by Audrey Margier, who's a postdoc here. Her paper is in review currently, but we see huge amounts of estimation directly above that part of the margin as well. Yeah.
Okay, we'll open it up to questions.
Hey, Pete.
I don't understand the counterclockwise rotation of the Abankai. Shouldn't it be the other way?
Pete's question was, I don't understand the counterclockwise rotation at the Abankai deflection. Shouldn't it be the other way? I don't think so, but we will find out. Yeah, so I think the idea that at least what Kevin Furlong and others have put out is that we have that this part of the margin is coupled with subducting less readily. That creates left lateral strain. So this is not subducting as easily. This is readily subducting.
Seems to me that if the Nazca Ridge is coupled with that plate, it should be dextral.
So I understand the question now. Well, I understand, I think, the confusion. So Pete said, I think it should be, if the Nazca Ridge is coupled with the other plate, upper plate, I think it should be creating dextral strain in the upper plate. I think the point that Kevin Furlong and others have made is that this is essentially, it's basically stuck to the bottom. And so it's holding it back. So, oh, I see your point. I'll work through that. I'll get back to you.
Other questions? Yes.
So the fork is submerged in the wake of the ridge, but KSN is still high and erosion rates are still quite high. I'm just wondering why that is. Are they high because they're transient and they're still high because they were being uplifted by the ridge, or they're just relatively high compared to like areas south?
Both. I think it's kind of a, yeah. So the question was about the KSN catchment average channel steepnesses, and basically the observation that they are steep north of the ridge, even in places where the ridge has already passed by. Why is that? Yeah, so I think it's kind of both that they're still readjusting, they're still trying to get back to their initial state. I also think that, you know, just relative to the south, which hasn't been perturbed by this ridge, it hasn't seen this uplift. That's just going to be a zone of lower KSN index. Yeah.
So the Amazon River originally ran into the Pacific. When did that get cut off in the port?
Okay, so the question was, the Amazon River originally ran into the Pacific. When did that get cut off? And was the second question, and where?
When did it, what time did it get reversed?
Yeah.
And the land use rose?
So the best estimates today on the reversal of the Amazon, well, I'm going to say reversal. It started flowing to the east at 9.8 million years, Karina Hoare in 2017. There's pretty much all of the estimates are converging on that. So the onset of the Amazon fan kicks off. There's a change in neodymium isotopes where they basically show a change from cratonic sources to Andean sources. The palynology changes in cores out there. So I think we've got it pretty well pegged that the Amazon system proper is established at 9.8. Why I hesitate to say reversed is around 10 MA, there's just this mega wetland system. It's called the Pebas wetlands. So there's not really any through going drainages proper. It's kind of this poorly organized system. Other folks have suggested that it drained all the way out to the Pacific. That's contentious. We can't find any basin records in the high Andes that show where that would have been located. But folks are definitely looking for them. Yeah.
So I have a question on your thermochron plot where you go from north to south and show the arrival of the ridge. And
Yep.
about 2 million years later, there's a peak in those cooling ages. You must have been generating a lot of sediment that was migrating southward along the margin. Is there any record of that sediment accumulation
Are you talking about within the trench proper?
anywhere in the forearc?
Okay, so the question was about the thermochronometric ages and that we've got this essentially big pulse of erosion that's propagating southward through time. Where are all of the sediments going basically related to this? So there are large deposits in the forearc that are Miocene in age, pretty thick sediment accumulation. There's also, related to the question that I just got asked about the Amazon River, the erosion or the sedimentation rates in the Miocene out in the whole Forelands basin system are really high as well. So all of the sediment accumulation really peaks at that time. So there's plenty of places where it could have been going.
Is there a record of like tectonic erosion or subduction erosion associated with the migration of southward migration of the Nazca Ridge
Yeah, so
of the forearc?
the question was, are there any records of subduction erosion changes associated with subduction of this Nazca Ridge? Yeah, so Peter Clift is the main guy. Peter Clift and Andrea Hampel are the two folks that have worked on this. They argue that there's been about 100, well, it's a volumetric calculation. They argue that there's large subduction erosion basically associated with this. Yeah. Which makes sense.
Yeah.
Sorry, can I ask a question?
For sure.
So I'm intrigued by the idea of you're saying that there's kind of heterogeneous coupling between the lower plate and the overriding plate, right? That's kind of concentrated in some areas and then kind of disperses out to a flat slab. I'm wondering, is there any correlation with modern, with sort of measured, observed aseismic creep in some of these regions, or is there any indication from, say, ocean bottom seismometers that there are heterogeneities in the sort of the seismic expression across these coupled areas?
Yeah, so
I don't think you need to
yeah, I
repeat.
think you probably got that one.
Yep.
Yes, there definitely are differences. So Susan Beck's group has worked on this and the kind of the state of stress above the subducting disparity, and there are definitely changes there. Other groups have done it, I guess, using other methods, and similarly, they see different states of stress.
Which way does it go?
Which way does it go?
Is there more aseismic creep above sort of the Nazca area, or?
They basically show that the zone above the Nazca Ridge is essentially seismically locked, and that the zones around it are subducting more freely.
Can I comment on that? Then I have a
Please.
question. Yeah, so it depends a lot what you mean by couple. If you look along the trench and the big magnitude 8 earthquakes, there's no correlation, like you have bigger earthquakes where the Nazca Ridge is subducting compared to north or south. But that's just in the upper, part of the big boundary. So that's always been one of those things that I thought, well, if these ridges are clogging things up, maybe they're going to be big asperities locked up and then have bigger earthquakes. That doesn't seem to happen, at least not for the last 500 years. And then in the crust above where the Nazca Ridge goes down, there's not that many earthquakes in the crust. But above the Sierras Pompeianas flat slab, there's tons of earthquakes, like, many tens times more in the crust. So I don't know exactly what that means in terms of deformation. It might be that the above the Nazca Ridge, Peru crust is much warmer. The earthquakes that are there seem to be a lot shallower than in the Sierras Pompeianas, where the crustal earthquakes are 35 kilometers in the crust, maybe even 40 kilometers deep, very deep. So I think there's a lot of room to pursue that more in terms of what's going on. But I really loved your talk. So now can I ask my
For sure.
other question? And this is maybe a little bit unrelated, but as you're talking, I was thinking about Carnegie Ridge, and I've seen some of the work on the uplift, but the Carnegie Ridge doesn't cause a flat slab, and it's another one of these huge, big ridges. So what's your take on that? You can
Yes.
speculate like everybody else.
Yeah. So the question was about the Carnegie Ridge, which we just looked at a couple of questions ago, and why it doesn't have a large flat slab associated with it. I would say that the geologists do not agree when this thing started subducting. Estimates on onset of Carnegie Ridge subduction range from 15 MA down to about 100,000 years ago. I think the 100,000 years is really on the low end of this kind of bogus, but real estimates start from about 2 million years ago all the way back to 15 million years. We don't really know what we're looking for in the upper plate in terms of what we should see, what the observables are, that then we can call upon to say, hey, there was ridge subduction. And so that means that every geologic change over the past 15 million years in Ecuador, people call on the Carnegie Ridge. So I think we need to figure out when it began subducting to say something about why there's no flat slab. Something I'm thinking about actively.
But the coast, as you said, is uplifted where it's going in.
What-
Terraces, there's-
What I would say is that even though it's not a true flat slab, the arc is remarkably far inboard, right? You have volcanoes that are sitting out in the Foreland Basin that are, the arc is remarkably wide there for as narrow of an origin as it is. And volcanoes span all the way from the Western Cordillera all the way into the Foreland Basin. So Reventador and others are just sitting way out in the Foreland Basin. So I do think that there's it's definitely shallower than it should be.
We were starting to see that inward migration.
Yeah, exactly. And perhaps it's just something that we don't understand, where it takes, a couple of million years for it to effectively extinguish, and we just haven't had that time. Who knows? Great question, though.
Yeah, no, it's fun to think about.
Yeah.
I don't know if anybody's plotted out the ages to see if there's any kind of a sweep. Arc magnetism.
Yeah, I
Where
heard.
the Carnegie Ridge comes in and maybe to the north where you don't have it.
Yep.
This is another conversation. Folks.
Yeah, for sure.
We'll talk later.
Hi, George.
Hi, great talk. I'm interested in what happens when your cat puts her head up into the overlying blanket. And so is it possible to think about a sphere of influence of bulging and uplift that's related to, maybe it's the viscosity contrast between the Nazca Ridge and the upper plate. And if there is such a thing, then you could sort of invert your distribution of erosion rates, seismicity, thermochron data to determine whether there's a kind of an uplift region that's moving along. And I don't know whether you could fix other boundaries around those ponds. But is it possible to think coherently and viably in the way that I'm describing, or is it just off the mark?
No, I think that's great. So George Davis asked the question, what if your cat has sticks its head into the, basically, what if there's a viscosity contrast between the upper overriding and downgoing plates, and could you basically contour your thermochron data or some other data to show kind of a sphere of influence where there's this migration of this erosional pulse or ridge coming southward through time? Yeah, so absolutely we can do that. My co-author Audrey Maggie Curry Ellis is much better equipped to do that kind of work than I am. So she uses a thermokinematic software called P-Cube. That was originally the goal with this, and then she moved institutions and we got sidetracked, and we were pretty happy with kind of all of these other data sets we got out of the geomorphology. And so we were trying to write it up as is. But long term, it's something that I definitely want to pursue, because I think you're exactly right. You should see this kind of sphere of influence migrating through time. And that should be quite quantifiable given the spatial distribution we have. Yeah. There's also supposed to be another like huge Peru thermochron data dump coming out from another group. And so it would, and theirs is mostly located, the Eastern Cordillera, where we basically have no data because nobody's published there before. And so that should be a huge benefit if we want to do something like that.
Maybe time for one last question. If not, let's thank Sarah again. Thank you, Sarah.